All right, let's talk about magnitude of a vector. The magnitude of a vector is the length of the vector. All right, so you could probably figure this out on your own with a little bit of thought, but we've got the formulas right here. It's hard to see in the picture, but you should be able to see it better on your note sheet. The magnitude of vector v can be found using the distance formula, because that's all the distance formula is. It tells you the length of a segment, and when we're trying to find the length of the arrow that represents a vector, we just use the distance formula. So if we've got 2 points, we drop it into the distance formula. If we have the components, so if we have vector A is equal to A comma B, or if we had, for instance, vector V, maybe that's -7 comma 5, or whatever, we can find the magnitude of that by using the Pythagorean theorem. You can see that in the triangle here. If I want to find the length of the blue arrow, then I would just take whatever the horizontal distance is, call it A, and the vertical distance, call it B, and we just use the Pythagorean theorem there to find the distance. Okay, so that's all that this is. So for this one, for vector V, we would do this. The magnitude of vector V, sometimes it's called the absolute value of vector V. That's why we use that symbol. So the magnitude of vector V would be equal to the square root of -7 squared plus 5 squared. Okay, so that's 49 plus 25. That's what, 60 plus 14, 74. Okay. Square root of 74 would be the magnitude of that vector. And that's all we mean by magnitude, is how long the vector is. And so I sort of just did an example here for you. Find the magnitude of vector v represented by PQ. So we're going to do a similar thing, except now we have the point, so we have to use the distance formula. So to do that, we'll write this. Vector, the magnitude of PQ is equal to the square root. We call this x1, this y1, this x2, this y2. Then we'll take x2 minus x1, so that's -5 minus the -3, that's +3 squared, plus y2 minus y1, that's 2 minus 4 squared. Do math, and I think you end up with, should have looked this up before, ends up being 2 square root of 2. Or whatever the decimal for that is, that'd be fine as well. Okay, to finish out this, this side of the note sheet, we're going to talk about scalar multiplication of vectors. Right, so anytime we are multiplying by a scalar, it means we're just taking the vector and we're scaling it. So we might double it in size, or we might cut it in half, or cut it by a third, or multiply it by 5 to make it 5 times as long. If we take that plane vector from the beginning, the vector was like 300 miles per hour straight north. So suppose that that's this vector here, 300 miles per hour. Right? Suppose that the plane is going to land and it needs to slow down to 100 miles per hour to land. Well, then what we would do is we would take this vector and we would multiply its components by a third. So we take a third of 300, and that would be 100. So it would be 1/3 the length. It would be 100 miles per hour, okay, in this direction. When we want to scale down a vector that's not so simple, all we have to do is multiply the vector by the components by whatever we're scaling it by. So for instance, if I had vector v is given by 2, 8, and I wanted to scale that down by 1/2, I would just take 1/2 of v, and that would be 1/2 of the components. Sorry, I'm running into the lines here. That will end up being 1, 4 for the vector that is, and that vector will be half as long in the same direction. Okay, so I want to go back to this another plane example here to talk again about scalars, but then also I want to lead into vector addition. So consider a plane flying straight west at 400 miles per hour. So let's first of all, let's represent this with a vector. So 400 miles per hour. Maybe that's a vector going straight west. It's this long. So here's your vector. It's 400 miles per hour. Okay. And actually, I don't know if you want to write this down or not, but we could write the component form of this vector. All it would be is 400, comma 0. Okay, it's 400 in the horizontal direction to the right, so it's positive 400. We haven't talked about this, but it's positive 400 if it's to the right. It'd be negative 400 if it was going east, because it's in the negative direction, and 0 in the vertical direction. So anyway, here's the vector that represents plane flying straight west at 400 miles per hour. If it slowed down to 100, what would the vector look like? Well, that would be scaling the vector down by a fourth, right? So it would be 1/4 the size. So I don't know, maybe there. Okay, so there's your vector that's 100 miles per hour. Okay. All right, next question. How would it change if there was a 50 mile per hour wind from the west? How about a 50 mile per hour wind from the south? So let's think about this. Draw a line here. 50 mile per hour wind from the west. Okay, well, if it's flying, let's see, what did we say? A plane is flying straight west, and it's getting hit by a wind that's 50 miles per hour from the west. Okay, so how fast will that plane be going? Hopefully you thought in your head 350 miles per hour, right? It's going 400 miles per hour without any wind, but now there's a 50 mile per hour wind acting on it. It is not speeding up or giving the engines more power to compensate. It's just no wind, it would be going 400. Now there's wind, so it's in fact 50 miles an hour of wind. So those two forces would counteract to give you a vector that is actually 350 miles per hour. So it's going to be a little bit shorter, 350 miles per hour. And that vector would be written like this, 350, comma 0. And so what we've done is we've taken the plane vector and we've added it to the wind vector, although the wind was going in the other direction. So it's like taking 400 plus a negative 50. So in fact, maybe you want to write that down. This came from 400 plus negative 50, comma 0. Okay. The next problem says, what if it was a 50 mile per hour wind from the south? Okay, so now we have a 400 mile per hour wind. Actually, let's do this. So we have a 400 mile per hour wind. It's getting hit by a 50 mile per hour wind from the south. So this is 50. So what's going to end up happening is the plane's actual path, like we talked about in the first example, the plane's actual path is going to be at somewhat of an angle, and it's going to be represented by this vector right here. Okay, that vector is not going to be exactly 400 miles per hour. It's going to change because the wind is pushing on it. Okay, so the horizontal component would be 400. The vertical component, though, would be 50. What we've done here is we've added two vectors. We've added the plane vector to the wind vector. We add those two together and we got the resultant vector here. That vector excuse me, can be given by 400, comma 50. Because it's 50 in the vertical direction, positive 50 because it's going up, and 400 in the horizontal direction. And we can figure out the magnitude using the formula from the other sheet, or the other side of the paper. Right? And so that's called vector addition, where we take one vector, and then we add the vector to the end of it. And on the slide to the right, or the square to the right, rectangle to the right, we'll explain that a little bit further.